Dear students, welcome to the course of Architectural Studies for Engineers. This is lecture number 24. I am your teacher Ravinder Kumar Khyani, Assistant Professor, Department of Architecture and Planning, NUT University of Engineering and Technology, Karachi, Sindh, Pakistan. As you know that we are discussing the topic architecture restoration and conservation and its impact on construction. In last lecture, we have seen cultural heritage and architectural monuments and its impact on construction engineering. Today, we will continue with the theme and learn about geometry of architecture and its relation with the construction engineering profession. How geometry and its mathematical equations has an impact on architecture and construction engineering. How built form or buildings and structures created by architects and construction engineers through geometry. The next thing that we learn is about the geometry and its impact on architecture and construction within Islamic societies and its detailed application in construction engineering and architecture of Islamic culture. Then we will view a case study of a building of a Moroccan court and learn how construction engineering practice is having a profound impact of architectural restoration and conservation. In this way, we will further develop our understanding about the impact of architectural restoration and conservation on construction engineering practices. So let's begin. First of all, we will see a video about the geometry in architecture and construction engineering. And we will learn how architects think about geometry and how do they apply it in the building construction practices. Let's learn how geometry and its mathematical equations has an impact on the architecture and construction industry today.
The three figures of the plane: the triangle, the circle, and the square. Remember? In 2500 BC, the pharaoh dreams of one of the wonders of the world, and through the creative line of the architect, the triangle becomes a pyramid, which is then repeated and redrawn throughout antiquity, the modern period, and the contemporary one. And now the circle, a line whose points are equidistant from the center. Observe its simplicity. It draws a Ferris wheel, which becomes a landmark of the City of London, a huge mirrored cookie in Abu Dhabi, and a pile of pancakes in a new library in Sydney. At last, the square. In a tri-dimensional world, the square becomes a cube or a cuboid. These are volumes that, through the ease of their representation, celerity of calculation, and of execution, they yield the most common shapes present in architecture. However, architects' imagination didn't just limit itself to the basic polygons. Over time, architecture, geometry, and engineering weren't deprived of coming up with new shapes and setting new challenges of representation and calculation. To help us understand some fundamental curves, behold a right conical surface. This conic surface is built based on a directrix, the circle of the base, and on the geriatrix lines. Let's now section it. Let's see. We position the intersecting plane. Let's start with a plane that will section all the geriatrixes. We shall obtain an ellipse. If we straighten this plane, making it horizontal, we get a circle, which is a particular case of the ellipse. Let's increase the incline. The intersection with a plane parallel to two geriatrixes results in a hyperbole branch. If we continue to tilt the plane till it becomes parallel with the G-line, we then obtain a parabola. A parabola is the flat curve defined as the group of points that are equidistant from a point and a line. It's quite simple actually. We come across this line in our everyday lives from shore to shore on suspended bridges in Portugal, the USA, in China. Let's now have a look at these three projects. The first, the Cathedral of Brasilia by the architect Oscar Niemeyer. It was built between 1958 and 1970, and each of the 16 reinforced concrete pillars weighs in at 90 tons. Next, we have the Sagrada Familia School in Barcelona. The little building, built in 1909, is a project of the last artistic stage of the Catalan Antoni Gaudi. And finally, the Oceanarium of Valencia, finished in 2002. It was the last work of the architect Felix Candela, who died at the age of 87 without seeing it completed. So what do these three projects have in common? The answer seems blatant, doesn't it? There are no straight lines, only curved meshes, right? Wrong. Or should we say, partially wrong? Okay, let's open a parenthesis here. In 2002, the Spanish architect and engineer Santiago Calatrava inaugurates Wave, a sculpture ordered by the Medius Museum in Dallas. However, Calatrava didn't just create a common sculpture, but rather a kinetic piece whose movement creates a wave. The curved surface of the wave is suggested by the synchronized movement of a series of 129 beams mathematically positioned. How does this all work? Let's check with history. Vladimir Shukov was born in 1853 to the then Russian Empire. In 1896, Shukov built the first structure shaped like a leaf hyperboloid, a 37-meter light steel tower sustaining a water reservoir on the top. Shukov is considered the inventor of a family of structural shapes, the one-sheet hyperboloids of revolution. So what exactly are hyperboloids of revolution? We'll need a hyperbole which will function as a geratrix. We'll need an axis, and now the hyperbole will execute a revolution around the e-axis. Let's make use of the GeoGebra through the GI al quadrado site to help us with the tridimensional simulation. The full revolution of the curve around the axis has generated what we call the one-sheet hyperboloid of revolution. And what about that initial question of ours? Is it just a curved surface, or does it contain straight lines? For each of the points of the hyperboloid, two distinct lines run through and are contained in the surface. So it's confirmed. The one-sheet hyperboloid of revolution combines the curve-shaped with a twice-ruled structure. It is now time to go back and contemplate Oscar Niemeyer's curves. Niemeyer said that what attracted him was the constraint-free and sensual curve, the curve he found in Brazil, in a sinuous river course in the waves of the ocean and in the body of the favorite woman. In Niemeyer, purity of architecture comes down to this simple gesture, a poem and a curve. In the Cathedral of Brasilia, in accordance with the concept of architecture, the shape and arrangement of the pillars represent two hands lifting towards heaven. Though while Niemeyer drew the ideal shapes which would transport the Catholic to infinity, Joaquim Cardoso, the engineer specialized in structural calculation which made the Brasilia ideas possible, pondered over the best hyperboloid which best solved both the architecture and the engineering, which best resolved concept and structure. Antoni Gaudí is one of the most famous architects in the history of architecture. His work primed in the use of organic and naturalistic, which in itself set it aside from the then architectural tendencies. His first work of art, the Sagrada Familia, is still today, 135 years after its start, in progress. Gaudí had a passion and a knowledge for mathematics and geometry, which allowed him to develop new structural systems without recurring to calculations. He tested his stress models in scaled-down models, which he then applied in his work. Gaudí was the first architect to use conoids in his work. Presently, and in his honor, they are called Gaudí-ruled surfaces. Let's now explain how a conoid is geometrically generated. We shall use as the directrix a circumference D. We'll use a line segment E as an axis. And finally the line G will be the geratrix and shall lean on the axis and the directrix, moving through them and generating the conoid. Let's make a second experiment. Instead of a circumference, let's use a sinusoidal directress to generate a sinusoidal conoid, the conoid that Gaudí applied in the wall and roof geometry of the Sagrada Familia school. Felix Candela was born in Spain, but at 26 he leaves for Mexico, where he takes up double citizenship. Candela had a special talent for geometry and an oath-worthy attraction for surfaces called hyperbolic paraboloids, with which he frequently resolved his architecture. Candela sustained that the geometry of this surface generated the necessary rigidity to enable the construction of blades with minimum thickness, the so-called cascarones. Built in 1951, the Cosmic Rays Pavilion, a small laboratory in Mexico City, was his first work employing this surface. This membrane of concrete was only 2 centimeters thick. So what is a hyperbolic paraboloid? Well, we'll need two non-complanar lines, R1 and R2. Let's run a third line, G, through the other two. Now all we have to do is move the G line at constant speed through the R1 and R2 lines, obtaining the twice-ruled surface. The hyperbolic paraboloid name is due to the fact that it has both hyperboles and parabolas as sections. Let's see. By sectioning this surface with the horizontal plane, we obtain curved lines which we verify as being hyperboles. Intersections with right planes will render parabolas. Let's return to those three projects, Niemeyer, Gaudi and Candela, and our initial question. So after all, the answer that seemed apparent wasn't. The three buildings are in fact curved surfaces. True. But in history, we have just witnessed that these curved surfaces in particular are ruled. They are surfaces capable of being generated by lines. In architecture, shapes, geometry and formulas entwine naturally from the idea to the construction. Mathematics is not an abstraction disconnected from reality, but a vehicle of the project. The creative design needs shape and rule. It needs a language that can provide its representation, calculation and execution. It needs geometry and equations.
So you have seen how geometry is applicable by the architects and it affects the overall construction engineering. Now let's go ahead and see another video, and it is about the geometry and its impact on architecture and construction practice in an Islamic society. It explains how complex geometry of Islamic culture applied in building construction practices.
In Islamic culture, geometry is everywhere. You can find it in mosques, madrasas, palaces, and private homes. This tradition began in the 8th century CE, during the early history of Islam, when craftsmen took pre-existing motifs from Roman and Persian cultures and developed them into new forms of visual expression. This period of history was a golden age of Islamic culture, during which many achievements of previous civilizations were preserved and further developed, resulting in fundamental advancements in scientific study and mathematics. Accompanying this was an increasingly sophisticated use of abstraction and complex geometry in Islamic art, from intricate floral motifs adorning carpets and textiles to patterns of tilework that seemed to repeat infinitely, inspiring wonder and contemplation of eternal order. Despite the remarkable complexity of these designs, they can be created with just a compass to draw circles and a ruler to make lines within them. And from these simple tools emerges a kaleidoscopic multiplicity of patterns. So how does that work? Well, everything starts with a circle. The first major decision is, how will you divide it up? Most patterns split the circle into 4, 5, or 6 equal sections, and each division gives rise to distinctive patterns. There's an easy way to determine whether any pattern is based on 4-fold, 5-fold, or 6-fold symmetry. Most contain stars surrounded by petal shapes. Counting the number of rays on a starburst, or the number of petals around it, tells us what category the pattern falls into. A star with 6 rays, or surrounded by 6 petals, belongs in the 6-fold category. One with 8 petals is part of the 4-fold category, and so on. There's another secret ingredient in these designs, an underlying grid. Invisible but essential to every pattern, the grid helps determine the scale of the composition before work begins, keeps the pattern accurate, and facilitates the invention of incredible new patterns. Let's look at an example of how these elements come together. We'll start with a circle within a square and divide it into 8 equal parts. We can then draw a pair of crisscrossing lines and overlay them with another 2. These lines are called construction lines, and by choosing a set of their segments, we'll form the basis of our repeating pattern. Many different designs are possible from the same construction lines, just by picking different segments. And the full pattern finally emerges when we create a grid with many repetitions of this one tile, in a process called tessellation. By choosing a different set of construction lines, we might have created this pattern. or this one. The possibilities are virtually endless. We can follow the same steps to create six-fold patterns. By drawing construction lines over a circle divided into 6 parts and then tessellating it, we can make something like this. Here's another six-fold pattern that has appeared across the centuries and all over the Islamic world, including Marrakesh, Agra, Konya, and the Alhambra. 4-fold patterns fit in a square grid, and 6-fold patterns in a hexagonal grid. 5-fold patterns, however, are more challenging to tessellate because pentagons don't neatly fill a surface. So instead of just creating a pattern in a pentagon, other shapes have to be added to make something that is repeatable, resulting in patterns that may seem confoundingly complex but are still relatively simple to create. Also, tessellation is not constrained to simple geometric shapes, as M.C. Escher's work demonstrates. And while the Islamic geometric design tradition doesn't tend to employ elements like fish and faces, it does sometimes make use of multiple shapes to craft complex patterns. This more than 1,000-year-old tradition has wielded basic geometry to produce works that are intricate, decorative, and pleasing to the eye. And these craftsmen prove just how much is possible with some artistic intuition, creativity, dedication, and a great compass and ruler.
So you have seen how geometry has affected the overall patterns in the buildings, and construction of these patterns is very important to be understood by the construction engineers. There is a great impact of Islamic geometrical patterns on architecture and construction engineering practice in Sindh, and we can see some examples of it. Now, this is like a patterns that you are looking at is of Badshahi Mosque Thata. Here you find different kinds of geometrical patterns are used and constructed in this building. And there is a use of color, there is a use of texture, there is a use of materials and different shapes and forms that is evident that you can see, and there are different kinds of elements that are developed, and these elements include arches, these elements include the domes and the internal design of these domes. And there are small tiles which are pasted here, and this is a very tedious work done by the local artist, and they do practice this. So construction engineering is impacted by this Islamic pattern, and it is quite evident. I can give you so many examples from Sindh where you find this kind of architecture is made and the internal spaces are decorated and designed in a manner that geometry is very much, you can say, applicable in our local context. So after looking at, you can see this is the Shah Bitai's Mazar in Bitsha, and you can see how intricate geometry is practiced here. Well, finally, let's go to another example, and let's look at the case study of building a Moroccan court. And we will understand that how construction engineering practice is having a profound impact of architectural restoration and conservation. There are specialized construction engineers and families who work for the architectural restoration and conservation. So construction engineering is being affected by the architectural restoration and conservation practices, and there are whole families working for such kind of projects. Let's see this case study and you'll understand what I'm talking about.
In 2011, the Metropolitan Museum of Art opened new galleries for its Department of Islamic Art. As a curator, I knew our visitors would experience extraordinary works of art created over the last 1400 years. But we also wanted to give our visitors an experience of space and architecture and to show something of the living traditions in the Islamic world. The result is the Patti Cadby Birch Court, a Moroccan court built inside the Metropolitan Museum over several months in 2011. It took a team of experts, from curators and historians to designers and craftsmen, of course, to make the Moroccan court, using traditional methods that go back to the 15th century. Our work began with a journey to Fez. The world has changed so much and traditional crafts are dying out very, very fast. But to the credit of the Moroccan government, they've taken this so seriously over the years that they've managed to preserve in Fez and other centers the traditional methods. Being so close to the moment of creation is something that has an incredible power, and it's something that profoundly moves you as a curator. In Fez, there were 40,000 craftsmen. We met with many guilds, many groups, and we did find potential to work with a number of different people. However, when we met the Naji family craftsmen, run by 4 brothers and their father, and then they have several workshops in Fez itself. At one point, Rida picked up Muhammad's hand. He said, "Look, this is my brother's hand." And we looked at that hand, and it was the hand of a craftsman. It was rough and calloused, and it had plaster all over it. He'd been chipping away since the age of 14. It was one of those moments when you just felt this was the right partner for you.
We are 7th generation in this business, but for me and for my family, it's unlike any other project that we ever undertaken, because this will serve as reference for scholars to learn more about the Islamic architecture.
I was employed as an art historian consultant to the project. I suggested having a medieval style courtyard. I have a very personal reaction to cut tile mosaic or zillage. Morocco, North Africa, is burning hot for so many months of the year. Visually, it's such a comfort to see blues and greens and cool colors, evoking nature and gardens and water. Perhaps it's because I grew up in a courtyard house with traditional decoration. I can remember, walking barefoot on tiles. In the Islamic city context, there is no facade. Houses are all stuck together, the streets are very narrow. The courtyard is the focus. It's in fact the facade, but it's on the inside, and it's very private unless you've got access to it. The Moroccan inspiration for the courtyard is the madrasas of Fez, and they are perhaps the best symbol of the intellectual and cultural life of the medieval Western Islamic world. The madrasa was a residence for students who formed the backbone of the education and political life, which will then serve to maintain the urban civilization as they know it.
As a designer and a landscape architect, I deal with outdoor space. When Navina came to me, she said, "Do you think we can do a nice Moroccan courtyard?" And I said, by all means. Most people who go to Morocco and look at the Moroccan architecture, they look at the court in terms of objects. The beautiful tile, the beautiful wall, but they don't look and see the space, the outdoor space and the meaning of the void and the mass. You see how elaborate it is, but how simple it is.
Traditional Moroccan architecture in general consists of a pretty formulaic set of materials that go from floor to ceiling. There's usually a marble basin, tiles surround on the floor. That extends into stone, and then you reach the walls, and the walls have a dado level of tile work, followed by elaborate carved stucco work, and then it goes and meets woodwork, and after the wooden ceiling, it culminates in a set of green roof tiles. What precise patterns and designs and colors do we put into this formula, and how do we adapt the scale of these courts that usually go on for 3 stories? into our very intimate setting without losing the spirit of the court.
What we've done is combine elements from the madrasas and houses of Fez and from Islamic Spain, houses and palaces of Granada. At that period, you can look at Western Islamic world as one cultural unit and craftsmen which move around between cities. So we looked at a tile panel from the Alhambra, which was exhibited at the Met in 1992. It's very bold.
If we were to adapt the scale exactly, we would end up with very big stars all over our walls. And we found that in general, the scale in Moroccan monuments is much smaller than the Alhambra patterns. So the challenge was, how were we going to reduce the width of that wide strapwork to make it suitable for our scale? The incredible thing we learned is that if you add a millimeter of width to your white strapwork, your stars become huge. If you take a millimeter away, they become small. It's incredible how much effect the width of the strapwork has on the overall pattern. In the end, we were all in Morocco, in the workshop, trying desperately to make this work out. The craftsmen themselves wanted to make it smaller. I was holding out for as much white as possible and not able to do it on the computer. We tried painting it on the wall, we tried printing it out in various stages. In the end, Achva Stein, our designer, took scissors and cut pieces of star and strapwork out and physically created a pattern to show us how the scale could be adapted. It was a very medieval solution in the end, and it was a very, very exciting moment in the whole thing.
You had to see the totality, the shape, the form, and the location. When you look at the wall, you see there are 70 different distinct pieces, like a puzzle fitting into each other to create the design.
We were working in Morocco for almost 6 months, in which we fabricated all the loose tiles for the zillige. The wood was carved in Morocco out of cedar from the Atlas Mountains of Fez. We used some of the best wood carver in the city, and it was very difficult in terms of the intricacy of the pattern.
We were convinced that the only way we would do this project was if the craftsmen actually came here. We wanted a direct relationship between the craftsmen and the walls of our Metropolitan Museum.
For us, we were transported back to the year 1300. It was clear to my team that we had to use only the elements and the tools that has been used for centuries. For instance, the plaster on the walls, they were smoothing it with their hands. When I look at this court, I see hands everywhere. Everything is touched by hands.
The Moroccan court exists in many contexts in Morocco, in a domestic setting, in a religious setting, and in a public setting as well. The inspiration came from all of these different types of courts coming together. Without making a historical reproduction, we wanted to be historically authentic. We had to do things very close to the original way. So we had to scale things down very precisely so that your eye wouldn't feel that things were wrong. Your eye has to have a sense of complete harmony when you look at these elements. The government of Morocco, for our project, released a special kind of stucco which they don't normally export. It's got a wonderful reddish hue, and you see this reddish color in Marrakesh particularly. Through the process of carving, they have to keep it moist, and it retains this soft and malleable quality for months afterwards. In fact, it's very fragile until it completely hardens. What's incredible is that if you make a mistake or you want to change something, you can just slap some more plaster on and shape it and carve it. It's got a kind of soft quality, and then at the same time it hardens just enough so that when you need to get your chisel in there and make it into definite shapes, you can do that as well. And then they have a series of tools. Some of them are as fine practically as toothpicks. And with these tools, they apply themselves to carving the surface of the stucco based on stencil designs that they have applied. There is a movement to the whole nature of the carving. They are able to create effects of leaves going over vines, under other leaves. They are extremely sculptural. It's an arabesque almost in 3 dimensions.
Living in New York for them was a challenge. I took them on a tour of the museum, and I took them to places to see what has been done before. The routine for 6 months was Monday to Saturday, and Friday we work until 3 p.m. and then they go sightseeing.
It's easy to recreate medieval designs, but difficult to get them in proportion with the rest of the space and relative to the other elements.
We had to act as extremely high patrons. We had to do things very close to the original way. In the old days, creation of these wall patterns would have been done with a lime-based mortar and done directly on the wall. But it burns through the skin and causes horrible injuries. So what they generally do now is create intricate mosaic tile pattern on a floor, upside down basically. The surface of these shapes is colored, it's smooth and brilliant, but the reverse of these shapes has to be cut into a particular beveled style so that they interlock well with each other. And then they pour into a concrete-based mortar, which allows it to get completely solid.
We had to get some variation of colors. For instance, 3 shades of blue, there are 2 shades of green, so it has the characteristic of an ancient antique panel.
We match the colors right back to the authentic palette of the 14th and 15th centuries.
There seemed to be a standard type of ceiling that was used for the madrasa courtyards of Fez. We thought that worked because it was so 3-dimensional and exciting. It has those projecting corbels, really add a bit of life to the surface. Although, of course, we've had to miniaturize the whole thing because we don't have much space.
It's a completely different scale. We needed to make the room in the proportion that will be adaptable to human scale, yet hint at the grandeur of Moroccan Andalusian style.
When the New York Times wrote about us, they were carrying the newspaper with them every single day. They became celebrities. And definitely was giving them this fuel to go above and beyond their capabilities.
At certain points, they actually departed from the design because they were so inspired to do better. Muhammad just said, I'm going to leave the design aside and I want to do something for you that I've never done before. That's going to be a freehand drawing based on a historical precedent. They have to have mastery over the symmetry and the geometry of these patterns. And it's the interlocking of these simple forms that leads to the complexity of the surface decoration that you see. It's very mesmerizing, actually. No matter how stylized it is, there is an underlying logic that does not break down. That's an important part of the heritage that they are keeping alive. Most craftsmen all over the Muslim world tend to be Sufis. Much of the work that they do reflects a kind of devotional spirit. For example, the craftsmen actually stylize the veining of the leaves to reflect the name of God. Allah, in Arabic script, is written essentially in a series of vertical strokes terminating in a rounded form. Very understated element in the decoration, but if you want to see it, it's there. To acknowledge that these spaces and this work has a spiritual dimension to it only enhances it and makes us understand how human beings are capable of doing things that require such dedication.
I think it's wonderful that people can visit a recreation of a medieval Moroccan courtyard without having to go there. is a real privilege for us as Moroccans.
This place is a constant reminder of harmony between two different cultures.
The strength of Moroccan design is to understand the beauty of the simplicity of the old world.
The Moroccan court will join a family of great spaces in the Metropolitan Museum, spaces that offer an area for contemplation, that transport the visitor to a completely different part of the world, and do this at the highest possible level with the greatest sensitivity to the surroundings and the masterpieces of the collection. It's a historian's dream, a chance to actually be part of the act of creating something wonderful.
Realize what kind of impact it has on the construction practices. So last but not least, I always recognize and acknowledge the people behind my lecture and the literature that I review. And in this case, in today's lecture, I've also gone through various websites to collect this videos as well as the images. And I would like to tell you that this is very important for construction engineer to, have a big team of workers, and you have to deal with all these, you can say, processes and the problems and issues that comes during the project. And in that project work, you are the leader. As a construction engineer, you are the leader. You can say, uh, arrange all this system, arrange all these people, arrange all these skills, materials, things, and make it a harmonious whole. Well, I thank you very much for listening to this lecture. I hope you have enjoyed and understood. And I will talk about other, you can say, uh, aspects of architecture that has impact on construction. And I'll also tell you about the many different buildings around the world and the people around the world who are working in integration, and construction engineers are basically creating wonders in the world. So we will see these wonders in next lectures. Wish you good luck. Thank you very much for listening, and good luck and goodbye.